Good morning. I'd like to thank the organizers from Amavea for inviting me to talk to you today. And what I'd like to share with you and what they've asked me to talk about is some of the techniques that we use for molecular detection of avian infectious bronchitis virus. So this is a brief outline of what I'm going to present to you today. We'll talk a little bit about the disease itself. We'll talk about detection of the virus by something called real-time RT-PCR. And I'm going to go over a little bit of the characteristics of this virus, different serotypes, what is the molecular basis of these different serotypes, so that we can understand how then we can use these molecular techniques to identify the type of virus that we have. And lastly, I'm going to briefly touch on some of the different types of this virus that are located. It says around the world, but primarily here in the Americas. So the disease itself is worldwide in distribution. It's a highly contagious virus. There are multiple serotypes of this virus, which makes it extremely difficult to control. Because we use modified live vaccines and in some cases killed vaccines, but because there's little to no cross protection between different serotypes, we have to select the proper vaccine to be able to protect against the virus that's in the field causing the problems. Now, this is a fairly mild upper respiratory disease. However, it becomes complicated. The typical signs are sneezing, tracheal rales, gasping, and coughing. We get in layers, we get a decrease in egg quality, and you can see the misshapen eggs, wrinkled shells. Some strains of this virus will cause a nephritis, and we'll get severe kidney lesions like this. The virus is highly infectious, very contagious, so the morbidity is usually 100%. However, mortality can vary depending on whether it's a nephropathogenic virus causing kidney lesions, which can increase mortality, or it's a strain or it's a disease that becomes complicated with other viruses, upper respiratory viruses, or bacteria like E. coli. Then we can have a much higher mortality associated with this disease. So the first detection method I want to talk to you about is what we call real-time RT-PCR. So this test, it's a molecular test. All it tells us is whether the sample is positive or not and how much virus is present in that sample. The beauty of this test is it's extremely rapid, and we can test a large number of samples in a very short period of time. It takes only about 20 minutes per test. We can do many tests at the same time, so simultaneously we can do 96 different tests on one machine at the same time. It does not identify type, okay? But it is quantitative. It determines the amount of virus in the sample. And real time means that it's just looking at how much amplified product we're producing as the reaction is ongoing. Okay? It's a typical PCR reaction, so we're amplifying a specific part of the viral genome, but in the real-time scenario, it's actually measuring the amount of product we're making as it's being made. So to just give you an example of how it works, this is what we're amplifying here. These two lines would be our target. We have two primers, a forward primer and a reverse primer, just like we normally do with any PCR reaction. But the difference here is we have this probe, and the probe is complementary to a part of the virus. It has attached to it a reporter, which will fluoresce when it's hit with ultraviolet light, and a quencher on this side of the probe. As long as the reporter and the quencher are both bound to the probe, we don't see any fluorescence because of the interaction between these two. So in the first step, the probe will bind to the target, and when this strand interacts